Hi, this is George Larakis again, and today I would like to discuss how to find volume by the method of cylindrical cells. So let's start as always with the when I use this method here. If you are in this point of the course, you all should know how to find the volume by using the method of disks. Just to remind a little bit what is this about. Let's say this is the Cartesian plane, and you have, let's say, this is a graph of a function f of x, and you want to find the volume when you rotate this around the x-axis, so that will give you something like this solid figure. And how we used to do that? We used to take small disks, that they have radius f of x, and we use the formula which we use for cylindrical disks, which is you have to find the integral of pi f of x square dx, and that's, let's say, from this point here, which is A, to this point, which is B. So that's this definite integral will give you the volume of this figure here. Okay, so and that's what we do when we do the method of cylindrical disks. But now let me tell you why we have to use this sometimes, the method of cylindrical cells. So let's say that you have, again, let's say this is the Cartesian plane, and let's say you have a graph of a function which goes, let's say, something like this. And you want to find the volume when you rotate this here around the x-axis. So this will be something like this. Approximately it will be something like this. But the problem here is that if you try to do it by using the method that we just mentioned before, you will have, let's say, for this delta x, this here, delta x here, you have two radius that you have to rotate. You have this one here, which is the inner radius, and you have another one which will come up to here, which it will be the outer radius. So which one you will use if you use the previous method? So that's the problem, and that it's that's why it's more difficult to do it by the previous method, and then sometimes it's impossible because usually what you will have here, if you wanted to break it down and do it by the previous method, you should, let's say, you find the volume when you rotate this line, and then you subtract the volume when you rotate this line here. So, but that's even sometimes is impossible because you cannot solve and find, what is the y for this part and what is the y for this part. I mean, let's say you have a third degree equation, then, it would be impossible to solve and find, what is the y for this, let's say, segment here and what is the y for this segment here. So now we are, let's say, at the point where we have to state it how. So, and of course here you have the first part, it's a brief theory. So let's say again, we have this here and you want, this is a graph of a function f of x, and you want to find the volume when you rotate the graph of this function around the x-axis. So what we do here is we break this into small cylindrical cells that they will be created when you rotate this thing here around the x-axis. So what you will get, something like this. So, like when you rotate this around the x-axis, you will get, this cylindrical cell, which, you can see it here in the 3 dimensions. And let's see what is the volume of this cylindrical cell. The volume of this cylindrical cell, if you open it, okay, this cylindrical cell, first of all, will have as a base a circle. This here it will be a circle, and the radius of this circle, it will be what? It will be y. Okay, the radius of this circle here, it will be y. So if you open, let's say this. If you open this cylindrical cell, okay, you will have, you will have a parallelepiped. So this here, let's say this side here is one. Let's say this side here is it will be when you open this. So that means that this side has this side here. How long is this side? This side here is because that will be the circumference of this circle, so that should be 2 pi r, where the r we said in this case is y. And the other side, which is this here, which will be this in our figure when you open it. How much is this? This is the x. So that means that this side here is the x. So what we have a parallelepiped that has the one side is 2 pi y and the other side is x. And of course, it's a very small the thickness of this parallelepiped. It's what? It will be you know, this here which we said that which it will be in this case dy. So that means that the thickness here, it will be, which is this here, it will be dy. So in order to make the to find the total volume, what you have to do is you have to break all this part into small dy's and add them up, and that will give you the total volume of the figure that we're trying to find. And of course, in this case, because we're talking about again a summation, that will be what? That will be the integral of all of these small parallelepipeds that we said they have volume 2 pi y, x, and you see here that the integral here, it will be in terms of y, because we are adding the volumes that they have thickness of dy, while in the previous method of cylindrical discs we were talking about dx. So, and of course, like the limits of this definite integral, it would be, let's say, this here it will be a, and this here it will be b. So that will be from a to b. So that's how we use the method of cylindrical cells. Now, are there any points of clarification? Yes, you can say that the only point of clarification here is that when you try to find the volume, when you rotate this around the x-axis, you have to find the integral with respect to y. While when we were doing it with the previous method, the integral was in terms of x. So that's one thing that you have to remember. And of course, if you rotate something with respect to the y-axis, if you use this method of cylindrical cells, here you will have x. While when we were doing the previous method of cylindrical discs, here it will be y when you rotate around the y-axis or an axis which is parallel with the y-axis. So that's about it. And now let's do an example. Let's say that you have again, this is the Cartesian plane, and let's say that you want to find the volume of the curve x equal with 2y squared minus y to the cube when you rotate this around the x-axis. The graph of this function here, you can do it by just taking some points, or you can do it with a graphing calculator, but it will be something like this. Okay, so, and you want to rotate this around the x-axis, the volume of this, it will be something like this. Now, we have to find, what are these points here and this point? What are these points here, this and this? they are the points of intersection of this function here with the y-axis or with x equal with 0, okay, which is the equation of the y-axis. So if you solve this system, which means that you set 2y square minus y to the third equal with 0. So this here, I mean, if you take y square as a common factor, you have inside 2 minus y is equal with 0. So of course, if you solve this, that means that either y is equal with 0 or y is equal with 2. So that means that, you know, of course, this here is the origin, and this point here has y coordinate equal with 2. So now, this is the formula that we have to use. And as we said before, when you are rotating with respect, when you are rotating about the x-axis or an axis which is parallel with the x-axis, here you will have this formula here, which means that you have to find the integral with respect to y. I mean, the limits here, they are 0 to 2. And you have to use 2 pi y. The x is this here. So you substitute the x equal with 2 y squared minus y to the third dy. So we have to find this integral here. So we can remove the 2 pi outside of the integral since it's a constant. So we can say that it's 2 pi from 0 to 2. And here if you do the multiplication, you will have 2y to the third minus y to the fourth dy, and I mean that's a pretty simple integral. So that's 2 pi times 2. The integral of y to the third is y to the fourth over 4 minus the integral of y to the fourth is y to the fifth, y to the fifth over 5. And now you have to integrate this, of course, from 0 to 2. So that means that once you substitute wherever y 2, and then you subtract for y equal with 0. So I mean that will give you 2 pi, and this here it will be y to 2 to the fourth. It's 16 over 4. It's 4 times 2. It's 8, and this here is 32. I mean 2 to the 50. 2 to the fifth is 32. So it will be minus 32 over 5. And of course, when you subtract the integral when you subtract the form 1y, sorry, is equal with 0, you know, all this will become 0. So that's the only thing we have. And you know, if you want to fix this a little bit more, you multiply this by 8, so that will be 40 minus 32, that should be 8. So 8 times 2 is 16 pi over 5. That's the volume of the solid that is created when you rotate the graph of this function here around the x-axis. And again, we have to find this by using this new method of finding volumes, which is finding volumes by cylindrical cells. So thank you for taking the time to view this video, and I hope you find it useful, and bye for now.